Hello everyone, welcome back and thank you for being back in the room on time. I do appreciate that. The next section is another very important section. It's Space Agency's Advancing ISRU. And we're going to hear from some new faces and some people that we know quite well in this world of space resources here in Luxembourg. I would love the speakers to come in even under the 10 minutes allotted to them, because then we will have time for questions. And I know we have a very active and interested audience. Even post-lunch, we have a very active, interested audience who may have one or two questions for you. First up, a great honor to introduce Jun Shimada from JAXA, and he is going to talk about study of a lunar ISRU plant and technology road mapping development. Jun.
Well, good afternoon, everyone. I'm Jun Shimada from JAXA. I'm a technical lead for ISL research at the agency. It's my great honor to be here sharing my studies with all of you. Thank you for making this happen. Where's the clicker? This is what I'm going to cover today. I want to start sharing the latest updates of Japanese space activities. As shown in we demonstrated pinpoint landing technology last year in STREAM mission. And what's coming next is Lunar Polar Exploration Mission, LUPEX in short. We're going to send 350-kilogram rover to the South Pole region to investigate water ice resources. LUPEX is a joint mission with Indian Space Research Organization in which they develop a lander for this mission. And multiple instruments on board developed by international partners, including neutron spectrometers developed by NASA and exospheric mass spectrometer by ESA. And the LUPEX is planned to be launched within a few years. And this chart shows the overview of what JAXA is trying to do from 2020s to 2030s. We plan to execute various missions, including MMX, which is a sample return mission from Mars and Moon. And in terms of lunar space exploration, lunar surface exploration, what we are trying to do is to promote human activities through development of pressurized crew rovers and mid-sized cargo landers. And through a lens of sustainability, space resource utilization plays a vital role to establish long-term human presence on the Moon. And given the limited budget and human resources, JAXA focuses on in-situ production of oxygen and hydrogen at this moment. To give you the sense of what we envision for the future, I will show you a 2-minute video, so I hope you like it. Is the sound available?
ISRU, to ensure sustainability of future space exploration. We put our focus on the study to produce hydrogen and oxygen for spacecrafts from lunar regolith at the ISRU plant on the Moon. As a first step, an excavator collects icy regolith. Then, a transporter carries it to the ISRU plant. Icy regolith is converted into liquid hydrogen and oxygen at the ISRU plant through various processes. Firstly, water is extracted from icy regolith by heating. Extracted water is purified and processed by electrolysis. Purified water is split into two gases, hydrogen and oxygen. Oxygen gas is cooled down to minus 183 degrees Celsius and stored as liquid oxygen. Hydrogen gas is cooled down to minus 253 degrees Celsius to be liquefied. Hydrogen is stored in the cryogenic tank to keep its liquid state. Liquid oxygen and hydrogen are transferred to the launch pad by transporters. Liquid hydrogen and liquid oxygen are filled into the spacecraft at the launch pad. Now waiting for the launch operation.
All systems are go for launch. 5, 4, 3, 2, 1. Main engine start. Liftoff.
The spacecraft is heading towards the new destinations on the Moon and on-orbit station. Water and oxygen produced from lunar regolith are also used for residents on the Moon. It's important to protect the natural environment when utilizing local resources on space frontiers to ensure long-term sustainability. JAXA never stops exploring and keeps challenging into the future.
Well, thanks for watching. Regarding baseline requirements, we set the target on propellant production as 57.6 tons per year based on JAXA's original estimation. And it should be noted, I6G's global exploration roadmap mentions that the target of propellant production is 50 tons per year, so it's fair to say JAXA's baseline is consistent with I6G's objective. And our current plan is to perform technology demonstration on the ground in 2020s and on the Moon in 2030s. We plan to produce 340 kilograms of water and 150 kilograms of oxygen per year from IC regolith as a first stepping stone. And based on the requirements, JAXA launched a series of research programs in recent years to investigate the technical feasibility of producing water and oxygen. The program covers from technology demonstration on core elements to integrated system design for ground demonstrations. And we made contracts with 3 major industrial partners in Japan, JGC Corporation and Chiyoda Corporation and Kurita Water Industries. Kurita Water Industries is doing experiments on water purification, making use of their competency and knowledge obtained by development of water recycling system on board ISS. The main objective of the conceptual study is to see if it's feasible to construct ISRU plant on the Moon. And based on the preconditions, we said the total mass of full-scale plant is expected to be 30 tons to 293 tons, including power facilities. Total volume of the plant system itself is targeted less than 33 cubic meters, equivalent to the capacity of 20 feet ISO container. These numbers greatly vary according to the mission design and technology selections. And in terms of on-site construction, modular construction method could be applied. The application of this method is seen in LNG plant on the ground. But a further investigation has to be done to explore practical ways for plant construction. Based on our study, the mass of the pilot plant would be less than 250 kilograms and 2 cubic meters. The power consumption is estimated to be less than 2 kilowatts at its peak. So if we can accomplish these numbers, it seems feasible enough to demonstrate on the Moon. This list shows several examples of key elements regarding in-situ production of propellant. And I don't have enough time to get into details, but we identified near-term priorities. We currently focus on upstream processes from water extraction to electrolysis. Water purification prior to electrolysis is one of the key challenges. In terms of future work, I think there are 3 elements. The first thing to do is to define system requirements, taking account of stakeholders' expectations, such as production rates, purity of the final products. Then flow down system requirements to subsystem or component level to formulate long-term R&D strategy. At the same time, it's important to define architecture level requirements such as power, CP&T, and transportation to strategize architecture development, which enables ISRU activities. Secondly, in addition to deepening our fundamental research for key technical elements, it's vital to develop integrated ISRU system on the ground to raise technical readiness level as one unified set of plant systems. And most importantly, I believe community expansion is the key towards the future of ISRU. And from a public sector's perspective, it's our obligation to stir imagination of present and future generations, providing opportunities to consider how to use their expertise in the realm of ISRU. Which is the reason I created a plenary session at ISC last year, specifically focusing on space resource utilization from technical and commercial perspectives. It was a big challenge for me, but I really had a great time with Jelly, Jeff, Catherine, Simone. I hope it made a little bit difference in space community. And lastly, here's my next bet. Jelly and I proposed a GNF event for ISC 2025 in Sydney. The theme would be the intersection of terrestrial mining and ISRU. This proposal is under review by IAF Program Committee right now, so please keep your fingers crossed so that we can get one more great opportunity to raise awareness of ISRU, bringing a breath of fresh air to ISRU community. Thank you.
Thank you. Perfectly timed 10 minutes, which gives me 1 minute for questions. Anybody got a question? Oh, yes, front row. Yes. We've got two very athletic people running around with microphones. But they've got to be sharp questions because we have a lot to fit into this hour.
Hi, I'm Razlan from Aphilia. We are developing wireless power for lunar application. So as part of the future work, so I'm kind of curious, is there any consideration for the power architecture system from the PV photovoltaics or to the ISRU plants? Is there any consideration what is the power architecture system looks like, especially for the transmission? Because at Aphilia, we are actually developing wireless power for lunar application. So I'm kind of curious about that.
Well, of course, the wireless transmission of the power is the method to produce the energy for ISRU power plant. But for ensuring high reliability, I think a wired option could be the first priority, and wireless transmission could be supplement at the first stage. Of course, if the time goes by, wired transmission could be priority in some near future. Thanks for your question.
My pleasure.
Thank you. Time for one more very short question. There we go.
Thank you very much for that very nice presentation. My name is Sebastian Rode, and you mentioned quite often that you are focusing on hydrogen and oxygen production. Could you maybe comment a little bit more on what type of electrolysis your JAXA is looking at, or is that already nailed down?
Well, we haven't reached a conclusion yet. We are doing doing a trade-off study, like PEM and alkaline method. So we haven't reached a conclusion yet, but it really makes an impact for the system mass and the power consumption. So we are looking into it.
Okay, thank you very much.
Thank you.
Thank you, and thank you for the talk. Thank you. And now from Polska, the Polish lunar mission, Jeremiasz, also known as Remy Merkel.
Hello. Okay. I'm trying to do my best. Here. Does it function? Not yet. Okay, it functions. Good afternoon, everybody. It's a big honor to be here among so many distinguished speakers and also so many experts on the audience. So I will try to do my best to follow this level. My name is Remy Merkel. I work as a senior specialist at Polish Space Agency. And today I would like to tell you something more about the concept of the Polish lunar mission, from concept to orbit, building Poland's lunar future. So here you have a really short agenda. I will introduce briefly Polsa and our vision for the space resources and describe the most important Polish lunar activities. And then I will go to tell you something more about the lunar mission consultation process, which was essential to formulate the mission objectives. and also what kind of Polish experiments were defined to be crucial during this mission. And then I will focus on the current phase, so it's 0/A, and we'll tell you something more about the scientific objectives and technological aspects of this venture. And finally I will focus to the future. Hopefully in time, because Lisa is watching. And so the most important, we are the governmental agency, project integrator, and public investor. The document which describes our aims and goals, it's a Polish space strategy, but now we have been developing the national space program, but now it's in government. And of course, we have many different areas of activities. The most important is to connect three really essential domains, so public administration, Polish research institutions and scientists, but also industry. We have international cooperation. ESA, of course, is our main partner. In 2023, we were able to increase our financial contribution to European Space Agency for optional program for 300 million euros. So it's a really significant thing, I suppose. But of course, we also cooperate with NASA JPL, for example. But I also really like this idea of CASA to also look for the new partners. And we are really open, of course. Also, space safety aspect, it's really important. We have Poland Telescope Array Network in different locations in among the world, like Australia, Chile, or South Africa. But also promotion and education are one of the most important domains. And I know that 5th of June is really important for iSpace, but I suppose that you can add one additional date for your calendar. In 8th of June, the second Polish astronaut, Sławosz Uznański, will go within the mission Axiom 4, Ignis, to the International Space Station to make really many scientific research. So please finger crossed for this venture, because it's one of the most important thing to our industry. And of course, we are also developing different space missions concepts, for example, Polish lunar missions. And here we have the most important field, like pillars of our lunar activities. So the first one is, of course, ESA, as I mentioned beforehand. So the European Envelope Exploration Program. There are also technology development elements. There are 6 concepts which are being developed, and 2 of them have a really huge participation of Polish entities. And there are also the small lunar missions proposals, concepts, and there you also have a really great involvement of Polish industry. The second one is the Artemis Accords. Poland was the 13th signature of this accord. And now we are looking for possibility of participating in the CLIPS mission, but also there is a proposal of Polish consortia to be able to participate in Artemis 3 mission and to to be able to capture the bright reflective lunar surfaces and also astronauts during the extra vehicular activities. And to do it, we are planning to provide some kind of 360 degrees field of view and also high dynamic range technique. And the third one is the Polish lunar mission, and I will be talking about it now. So everything started in 2021 when we were trying to develop a concept for innovative technological project, some kind of feasibility study. And then we chose the mission Cognition. It's a robotic lunar mission. And based on these effects of this project, but also based on our internal studies and of course the, let's say, international trends, we decided that Moon is one of the most interesting celestial body. And we started the process of consultation within the Polish space industry, within the Polish space ecosystem. And we are trying to involve as many entities, as many scientists, as many companies from the industry to gather their information and point of view about this mission. And finally, we are able to capture or gather ideas from more than 20 entities and organize different individual and combined meetings, in total 20 hours. But if you count the involvement of the, for example, employees of the Polish Space Agency, it would be probably the hundreds or thousands of working hours. And based on it, we were able to identify the 4 scientific research concepts, which are relevant to the Polish industry. But also one of our, the most important goal was to develop the Polish capabilities within our industry. And here you have the most important for Polish experiment concept. The first one, infrared spectrometer, to enable the remote sensing of mineral deposits, and of course to enable finally the in-situ resource utilization. So it's one of our strategic direction. The second one is soil mechanics, but also study of the moon's atmosphere. So also research is connected with the regolith. The third one, astrobiology, the growth of microorganisms in this kind of the microgravity conditions. And the fourth one, the miniature laboratory for studying cancer cells. So you can see that these domains, these areas of expertise are quite spread, or like quite wide. And now the most important slide of my presentation. So I will tell you about the Polish lunar mission phase A. Basically, it's a project which is being done by consortia of 5 companies. 4 are from Poland, but 1 is from Luxembourg. So it shows also the importance of the international cooperation. And of course, the main scientific objectives are the identification of lunar Mars with the highest potential in terms of the presence of different metals. For example, iron, titanium, copper, nickel, or platinum group elements, but also to identification the abundance of different gases, like for example, helium-3, oxygen, or others. And of course, it will be in line with the identification of strategic location for the establishment of lunar crew bases. And to be able to provide this data, of course, we will be doing some kind of the high resolution map. And the main objective is to be able to do it in less than 10 meter per pixel. So probably it will be really amazing resolution to be able to conduct all of these researches. And of course, also we are planning to do a great science within this mission. And there are a few of the most important scientific hypotheses. So the first one, we don't know yet how diversified is the abundance of the different elements and its concentration within the lunar regolith. So it's one of the most important aim of our mission. The second one is to also try to establish the potential abundance of the helium-3 based on the ilmenite because it's correlated. The third one is the distribution of water, but also hydroxyl group because it will be essential to capture or gather the really valuable elements in the future. The fourth one is the estimation of spatial distribution of different elements, but also evaluate the thickness and volume of lunar regolith, of course, in which contains the water, but also this hydroxyl group I mentioned beforehand. And the sixth one, as you know, the impact processes are the most important in case of the geological resources in the moon or in the space in general. So also we'd like to maybe go a little deeper to establish these features. And of course, also some technological aspects will be done during this mission. So we will choose the proper launch vehicle. Then, of course, we will create the satellite bus and also add the payloads. As I mentioned beforehand, for sure, the scientific instrument to enable the imaging within the visible light, but also infrared spectrometer are some of the most important payloads. But we are also open and looking for different opportunities, like, for example, tear spectrometer, fear spectrometer, or other additional payloads. And of course, also orbital demonstration, orbit determination will be really important for us, and providing the accurate ground station to enable the smooth and proper data analysis and integration. And all of these activities are in line with our strategic vision. And in March 2025, so a few weeks ago, we started the phase A. We will be trying to finish till the end of this year. So it's a quite intensive time in front of us. And of course, we will be trying to make a technology verification during ESA missions, but also Artemis 3 mission and also commercial missions, as for example, CLIPS. And priority is to put the Polish orbiter in lunar orbit in 2030. So we will be working really hard to be able to make this aim. And in the future, of course, it's a possibility to also put the Polish rover or maybe Polish lander, and it's the future. And all of these activities are in line with the emerging trends as in situ resource utilization, lunar infrastructure, astronomous mobility, and crew mission. So thank you very much for your kind attention. I have a really flashing over time, but hopefully it's not too late. So I will be really happy to answer all your questions or queries. Thank you.
Thank you, Remy. Thank you. Well, I think you should take center stage. Yes, we are on a very, very tight time scale, but are there any questions for Remy? Yes, we have a question here at the back.
The national Polish mission that you just talked about, is that something that you would plan to develop on a national level, or is that something that you would look to the ISA program to implement?
We are looking for synergies, but in fact, the main concept would be developed within our agency's capabilities. So, but of course, we are trying to also be in contact with different other projects. So it's some kind of really essential for us to find the synergy.
Thank you.
And but, the last comment, but we would like to make all phases, yes, within this project.
Another quick question? Ah, yes, Clive.
Very interesting mission, looking at many, many resources. You said at the end that you're looking at the poles and the water ice. With the capabilities you listed, that may be an issue. How are you detecting the water ice at the poles?
I have a scientific team behind me, but I suppose that they would like to, let's say, measure the regolith and also identify some potential water content within it. But we have been developing the concept of obtaining these elements from and of course the more geological surveys need to be done.
Yep, absolutely. Happy to talk to you afterwards about this.
Perfect. It will be really nice.
Thank you very much from the geologist. I love that answer to the question. I have a scientific team behind me. That's a wonderful answer. Thank you very much. Thank you, Remy. Thank you. And now, Francesco Latini from the Italian Space Agency is going to talk about lunar regolith as a resource and updates on the Italian Oracle project for oxygen extraction.
Hello, everybody. Okay, do you hear me? Yes. Thank you very much. It's a great opportunity to be here. And in the next few minutes, I'm going to give a very quick talk about the Oracle project that the Italian Space Agency is funding. And just to be thorough, the Oracle project fits in a bigger picture that is the initiatives that ASI is leading for the exploration, in particular of the moon, of course. And you can see it here. Oh, okay, no, sorry. I don't know. It doesn't have a pointer. Anyway, it's right in the middle. And before going into Oracle itself, just reminding what we are here for. So the importance of ISRU technologies for extracting either water and oxygen for usage of consumables by astronauts, as well as construction materials that could be used as protective layers against radiation and thermal insulation, as well as building tools for everyday use. And in particular, so ASI has been very into how it is possible to extract oxygen from regolith, which today, so far, could be considered maybe the only possible reserves among the possible resources that we can find on the moon. And in particular, we have a process that we've been studying. In fact, this project started with under a contract with ESA, and then ended. So together with Polytechnic of Milan, we've been taking the, let's say, the knowledge about the carbothermal process and its advantages of being agnostic to the regolith that is being processed, and trying to build a smaller payload, which is considered as modular because it starts with, you see the orange box here, with the main process, which is the carbothermal thermal process itself, in which carbon oxides are produced from regolith, from heating regolith and some reactants. And then possibly they are converted into water vapor and then into water. So the main characteristics, you can find them there. It's 15 kilograms, supposedly, depending on which launch provider we're gonna end up with, and the cost, of course, related to the launch. Before going into more technical details, this is the Oracle roadmap. Of course, it should be more and more talked about. I'm just going to highlight the fact that there are 3 different lines. The one, it is the scientific branch, which Politecnico of Milan helped us in doing with a contract of phase A and B1. And later, they will provide the scientific support for the initiative. Then I have I want to highlight the yellow line for the industrial procurement for phases C, D, B2, C, and D, and later phase E, that will bring to the launch foreseen in 2028-2029. And of course, related to this, there is the identification of the launch provider, which we started, which we have started some time ago, and hope to define by the end of this year. The whole project is entirely funded besides launch, so it is something that ASI really wants to achieve. In particular, I'm just going to give a little details about the scientific and engineering achievement that Politecnico of Milan provided. In particular, regarding the identification of the mission scenario and the preliminary configuration of the system, as well as some budgets related to the mass, the volume, the energy, the power, that will be needed for the process to take place. And finally, some of the possible programmatic and technological risks that we will, let's say, hope not, but we will face. From the scientific point of view, instead, that's the main goal that Politecnico of Milan will proceed in doing, in pursuing when the industry starts the procurement. Of course, the fine-tuning of the process parameters to regulate the yield of extraction and possibly optimize it. And in particular, also the effect that some parameters like temperature, reactant flux will have on the overall yield, as well as possible effects of the regolith granulometry and how each species contained in the regolith could contribute to the overall yield. In this context, in fact, we have that the parameters have a great effect from models. So we have that the whole process takes place at 1100 Celsius degrees, and 2 phases are alternated, one in which methane and hydrogen are fluxed together into the reactor, the other in which only hydrogen is fluxed to prevent coke deposits that could slow down the reaction. The yellow alternation scheme is the one that from models seems to be better. Of course, tests are ongoing to confirm and possibly refine that result. On the other side, we have that the different species contained in the regolith, possible batch, have different contribution to the overall yield. So 5 different species have been tested separately, 50 grams batch each, and you see the results there. Of course, these are preliminary, more tests will be done, but still we have that ilmenite and basalt give the most contribution, the others a little bit less. It is important that now to understand what all these needs, what are the needs in order to start the procurement and to consolidate the configuration. And regarding this point, that is the timeline for the industrial procurement, and you see that we have a SRR supposed to be at the end of this year, and according to this we divided some of the needs that we have to the provider in order to select the best option for the launch. I'm not talking about all of these. I just want to point the red block, that is the effects of the presence or not presence of a robotic arm to collect regolith from the lunar surface, because of course this will largely impact the design. So if this is a service provided, of course it will be better for us, as well as how much in terms of mass and volume we can launch and the related cost. Regarding this point, a robotic arm is a very key trade-off that we are studying, because depending on where we are and how we are collecting regolith, things can change. In particular, the best option would be to be the rover to scout and collect regolith and bring it back to the payload, such that we will use pristine regolith for the process. Of course, we can be placed on a lander, and then some studies suggest that the plume impingement effects are not that slowing down the reaction, but of course we will evaluate largely those aspects in case we are following that way. Otherwise, we could be placed on either on the surface of the moon and powered by the lander itself, or collect the regolith somehow by ourselves. Some studies have been performing in ASI regarding the possible strategy to collect regolith from the lunar surface, so everything is synergetic in its context. Just to conclude, some take-home messages. The Italian Space Agency is very involved in these ISRU activities, and we chose the carbothermal process because of it is agnostic to the regolith composition, and so the landing site. We are still evaluating the process parameters, and the launch foreseen in 2028 is compatible with the schedule of the industrial partner that we have been selecting. And the main trade-off is the one I just talked about, so I'm not saying it anymore. Thank you very much.
Thank you, Francesco. Thank you. I just want to leave time for questions, and we have Jerry. I think it's Jerry's hands going up right up. Even though you might as well jump on stage. You're the next speaker anyway.
Jerry Sanders, NASA. So you mentioned both the methane and hydrogen were going to be fluxed. I'm not familiar with that term. What does that mean?
Yeah, there was a slide. Anyway, oh, can I? Yes, thank you. Basically, we are foreseeing in the alternation scheme a mixture of 15% methane and 85% of hydrogen to be fluxed in the reactor in the mixture phase, lasting, for example, in this case, in the yellow case, for 3 hours.
Okay, so you're basically fixing or playing with the mixture ratio.
Exactly.
For how long?
Exactly,
okay.
And this is also another trade-off, because that percentage here is not, I mean, this is the baseline right now, but it can be 10-90 or 20-80, depending on which ratio gives us the best yield.
Okay, I just wanted to verify that you weren't turning it into a plasma or something like that.
No, sorry. Flux meaning.
Any other questions? I think it's James. Again. He should almost have his own mic also.
Thank you. The carbothermal process in Oracle, my recollection is that it's a little bit novel in that it happens at lower temperatures than you would normally use for carbothermal. And I recall some analysis in the past that as a Gibbs free energy problem, it doesn't look like something that should happen spontaneously. And I wondered what work had been done to verify that the model that you have is producing the results that you're getting the results you expect from the reaction.
Okay. Regarding this, I mean, the model, of course, from the free energy suggests something like this. But anyway, from the tests that we're performing on either simulant like the NU LHT in different, of course, masses, as well as on different minerals that we used as test simulants, following the same process that I just described, give us actually the yield. So it's true that the temperature is a little bit lower, but using the methane instead of just hydrogen increases the yield by tests right now. So we'll confirm this in the following period.
I think we have one burning question here, which I'll allow because I can see the eagerness in the arm.
I hope I answered the question, James.
This is beginning to turn into a PhD viva. But
Thank you very much for the presentation, and maybe connecting to the previous question. Are you sure that you are not focusing on one specific element, oxide, during the reduction, e.g. iron, if you, for instance, look at the ilmenite and the others?
Yeah, I mean, the CEO, I mean, we are, the reading here is about carbon oxide, is what the gas chromatographer gave us. There could be also other products of the reaction. Right now, we are not considering them, but it is something that we are foreseeing also to understand, not for this plant, but for future uses, if there could be other possible products that could prevent either the reaction or could cause any damage to the plant itself.
So you did not do a post-mortem analysis of the solid phase with respect to the oxidation state?
It is something that we are in plan to do for later tests, of course, yes.
Thanks.
I'm going to save you from any more chemistry. Thank you very much indeed. Thank you. They will reach you. They definitely know where to go. Jerry, you've already given us an overture to your voice. Please join us on stage. Jerry Sanders from NASA.
Thank you. I'd like to thank Catherine and the organizers for allowing me to be here. It's an honor to talk to all of you. This conference has been getting bigger and larger and more important every year. Unlike other, unlike other presentations where I tell you what we're doing and where we're going, not as easy this time. And I actually thought about every now and then looking back in time and actually taking a snapshot in what progress that we've actually made. And so with the remaining 8 minutes, even with my chartsmanship, I can't cover all of 2019 to 2025, but I will start giving you a sense of what our accomplishments are. I plan on writing a very detailed paper for IAC, so hopefully that will go into it. But we start looking back and how we've evolved our intent for developing ISRU. And I'm really pleased that we kind of changed from earlier in my career from a very government-led activity of this is what we're going to be doing, here are the RFPs for what we want to do, to turning it more into an industry effort to basically how do we actually help achieve industry to be successful. And so our plan basically has been more along the lines of not just what are we doing now, but where do we want to go 10, 20, 30 years into the future? And that's where this idea of industrialization comes in. So we've worked on market transparency, we've worked on the technologies and the system developments, and we've started to try to work on how do we start infusing these technologies into different missions. And so the bottom basically shows kind of the functional blocks of ISRU going from destination reconnaissance and all the way to developing and processing those resources into products. And I'm just going to highlight a few of those things here today. So first of all, how we do things. I came from the Human Exploration Program originally, and our ISRU project was fairly straightforward in the fact that we had one project, we were given a budget, and we had to do a plan based on that project and the funding that we got. Transferring to Space Technology Mission Directorate was very different. We did not have necessarily one project. We had a number of different types of solicitations that we could go to. Everything from early stage, early career NIACs through small business innovation to technology maturation and eventually tech demonstrations. So we spent a lot of time working with each one of those solicitations trying to find out how each one of those different areas would advance ISRU and what constituencies. And we made a concerted effort to really bring in the public and universities through challenges. And some of those have been fabulous. The last one that we did, Break the Ice Lunar Challenge, was amazing. And we had several companies do very well on that one. Another thing that we've spent a lot of time on is obviously the resource exploration. And here's a chart of potentially the missions coming forward that have been performed already and will be performed that are aimed at understanding resources to one extent or another. A lot of instruments have been developed. We've taken on the notion that this is not a single mission, but it's a campaign to understand those things. And we've had a lot of good and not so good situations. If you look at the chart, all those missions in red have failed, which kind of points to the fact that we need a lot of resiliency in our mission planning. If all those had been successful, then the knowledge base that we would have today would be much different than where we are. And so that last bullet that basically we need a resiliency in our measurements and our missions has become more and more apparent over time. I do want to go back in time to an earlier part of my career where actually during the Constellation program, we did a significant amount of development activities for lunar ISRU. We tested 3 end-to-end breadboard systems in Hawaii, 2 hydrogen reduction, 1 carbothermal, and we worked with our international partners, in particular the Canadian Space Agency. And we advanced the technology readiness level to, I would say, 4 or 5. We were about to start getting into vacuum chambers when the Constellation program was ended. And I kind of bring this up in the fact that, you know, all that work kind of sat until we came back around to the Artemis campaign and had to pick things up. And so since we have picked up, we have invested tremendously in oxygen and metal extraction technologies. At this point, we've developed 8 or invested in 8 different approaches, techniques. I would say that the highest technology readiness level is carbothermal reduction, and I'm actually going to give a presentation in the next session on that one for my colleagues. We are basically, I would say, at a TRL 5, getting on possibly TRL 6. That said, one of the things that was at a very low TRL at the beginning of the Artemis program was molten regolith electrolysis. And I have to say, over the last 5 years, we've made tremendous advancements in this. 2 companies in particular, Lunar Resources and Blue Origin. I know Blue Origin's in the audience. Lunar Resources actually tested a fairly large-scale reactor, 25 kilograms of regolith, in a vacuum chamber and performed their first molten regolith electrolysis test in lunar vacuum. I won't take any credit for anything that Blue Origin's doing, but they are advancing tremendously as well. That said, we have invested in quite a few others. 2 major points that I'd like to point out is that what's really exciting, and this kind of comes to Jim Caravallo's comment this morning, a lot of these technologies have applications for Earth, whether it's clean iron or the fact that if we can extract aluminum from an orthosite, that's an alternative terrestrial source than bauxite for aluminum mining here on Earth. The other thing that has excited me over the last 5 years is more and more money is coming in from venture capitalists and public-private partnership aspects that has really changed the game in comparison to the Constellation program. Polar ice, we've invested in 3 different mining technique options. looking at excavation of loose and hard excavation of icy regolith. The Break the Ice Challenge was very important on that one. And I would say that from a success-failure point of view, we've had some fairly good success on the regolith reactors and closed reactors like the Lunar Auger Dryer, as well as the PVEX from Honeybee. The subsurface heating dome approach does not seem to have worked very well, but that could possibly be because of the types of simulants that we've been using. Water capture and cleanup and water electrolysis, those were mentioned. We actually are looking at 3 different water electrolyzers, the proton exchange membrane, solid oxide, and alkaline. Each of them have pros and cons in terms of complexity and performance and how clean does the water need to be. And we haven't made a choice on that at the moment, but we have made significant benefits. Major takeaways, sorry for going over time. We've done a lot of work in the last 6 years. Resource exploration has gotten better, but we need more work. I think we're on the cusp of flying oxygen and metal extraction, and we really, before we dive deeper into water mining, we do need those resource assessment activities, and thank you very much. And
Thank you, Jerry. Well, I'll leave you. You're doing very. You're continuing your theme of very, very intense slides. I know it's. If there's one thing we know about you, it's certainly this. Any questions? Oh yes, we have a question over here.
Good afternoon, Szymon Murzyn, Mainboard Company. My question is related to the metals production. Can you please clarify what's the capacity for the iron production from regolith? And as well, can you put it in the context of uneven iron distribution in the lunar regolith?
Well, I mean, when you talk about iron extraction, you really have to vary between the mare and the lunar poles. If you have an ilmenite concentration, you can get a fairly good production of iron. And you possibly through any of the methods that I mentioned. The problem with highland regolith, polar regolith, is that the iron is at a much lower concentration, and it's typically bound to oxygen and silicates. So it doesn't break down and separate as easy. So when I talk about, so when you do molten regolith electrolysis, the first mineral that gets reduced is the iron. So you'll have a pool of iron with basically some silicon in it, iron silicates. How you tap that off and process it afterwards, that's one of the functions that both Lunar Resources and Blue Origin are looking at.
Just to follow up on the question, are there specific numbers? Because when we are talking about the oxygen production, usually we are able to tell how many kilograms per year are we able to produce.
Well, again, that goes to the process. You know, each process will extract oxygen at a different rate, and James talked about Gibbs free energy. So how much energy do you want to put into it? Some of the techniques that we've looked at is vapor pyrolysis, where you literally can separate everything and collect it. So, you know, step one is what's the concentration of those minerals and elements in the regolith, and then step two is what process are you using to extract the oxygen and subsequent metals. So there's no simple answer to that.
And we have another quick question in the front row here. If we can get a mic quickly to the front row. Thank you.
Hi, it's Sebastian, Jerry. Thanks for the presentation. I'm not sure if it's a quick question. I'm not sure if it's a quick answer, though. If I recall correctly, you mentioned industrialization at the beginning, and I love the way it's been put across with all the different elements. And at some point, I got a little bit lost with all the technology stacks. Would you briefly be able to outline how do you see the future of a functioning lunar economy within the scope of the work that you presented today, which was very fascinating?
No, I don't think you can do it briefly.
No. Yes, definitely over a beer. Just quickly, going back to the first chart where I said NASA's job is to enable industry. So to some extent, we've been looking at, well, what are the suppliers and who are the customers? What do they want? That leads us to examine different technologies that we might be useful to do. So as was mentioned, if I'm just looking at oxygen, I can do certain things. If I'm looking at iron, another. If I'm looking at aluminum and silicon, whatever else. So our job has been to basically try to pick winners to some extent and keep moving those forward based on whatever customers we can identify downstream.
Thank you.
Thank you very much. Thank you. I know you're back up in the next session, so we'll give you a little bit of a moment to just relax. And thank you very much. Yes, Jerry Sanders. And next up, we have our very own Larry Kuchko from ISRU, who's going to talk about ISRIC commercialization. Larry. Where is the mic? On the chair. Either, as you wish.
Hello, good afternoon, everyone. I will try to make it fast. So first of all, the idea is to discuss a little bit about what we are currently doing at ISRIC in terms of commercialization. We have heard a lot of discussions right now. We see that the purpose of business is very important for all of you, for startups, for researchers, for industrials. As a brief recap, what we are doing currently at ISRIC. As you know, I don't want to repeat what my boss has said. We are doing research, deep research, testing capabilities for the future. We have community activities, and of course we have commercialization activities, mainly two major programs, an incubation program, the startup support program, and of course an acceleration program, the BSGN, part of the BSGN, which is the Space Resource Accelerator. Our value proposition, if I may use that word, is to provide technical equipment, capabilities, testing, and even bigger in the future. Funding support, that's important for a lot of companies, how you will fund your activity. And of course, connecting to a national ecosystem, a very innovative ecosystem in Luxembourg in the field of space resources. So what are we doing? As I said, we are doing commercial workshops to engage companies, early stage companies, and well-advanced business companies in the field of space resources with our main partner, the Technoport, business and technology-driven incubator, through incubation program and acceleration programs. We need to distinguish a little bit the difference between both. I will leave it to you to read the slide afterward, but the idea is to say that we have two major programs to target a bigger scale of potential business, I would say, operator in the future. The incubation is for mainly early stage companies, and the accelerator is for larger companies. The scheme is a little bit different, but I will dig into details in additional discussions we can have afterwards. But the idea is to say that both are providing you value to operating a company in the field of space resources. The Startup Support Program, you often heard about that. So it's an incubation program run mainly in 3 steps. A phase 1 in 3 months where all the companies stays where they are in the world. So it's a worldwide outreach programs. Then in phase 2, one is selected and get the funding to operate in Luxembourg. So they have to be located in Luxembourg. And the third phase, which is an incubation period, post-incubation program, or program about 12 to 24 months, they have a business-driven applications in Luxembourg. And of course, every phase has its own specificities. The first one is mainly a de-risking approach, and the second one is mainly a prototyping or at least identifying the future business activities. This is our long-term roadmap. We have finished the 5th cohort, and we have 3 main programs left. I will say a word at the end for the future, call for application, because I have seen and heard a lot of companies interested by having a program benefiting through our potential funding support. At this stage, we have 5 companies located in Luxembourg. Terra I from Poland, Latini Space, you can see them on the booth, from Czech Republic, Space Backend, and of course, Neamine and Tumi Robotics. And of course, the SSP5, the 5th program, has selected another one and will announce the winner later on. The second program, the acceleration program, which is mainly for scale-up projects, it's kind of a matching of existing budget with ESA budget. We have heard a little bit about today. So again, there is an application phase, a phase 1, which is a support for a certain time of periods. So we're providing technical support, in-kind funding support to RISE investors, and of course, we provide dedicated support to all of the projects to get through an implementation phase and benefit to a specific funding scheme. The 6th project which have been selected is the one that you have heard this morning, so I don't want to repeat too much about that, but it's just to give you an overview that this one is more ESA member state operators, and for the incubation program, it's mainly on worldwide outreach. The global strategy, the ISRU strategy, what we want is to really integrate the entire cluster, from early stage venture to more scale-up developed product, starting with synergies, creating venturing, as I said, business commercially driven workshop, to see how this project can be related to an incubation, to a scale-up, and potentially deeper projects before being totally sustainably cash flow independent, I would say. Who we target? Terrestrial players, space players, cislunar players, and tomorrow ISRU players. The idea, as I mentioned, is to consolidate the full value chain of applicants, that the customer become the supplier of the other part of the member chain, of the supply chain, but that everyone is collaborating between each other. That's really the main outcome of the commercialization department. This is an overview of the project that has been incubated so far in Luxembourg. And the benefit we provide is really deep. Funding support, technical support, IP support, often neglected, fundraising guidances through our different experts. I will say a brief word after that. And of course, our incubator support, the Technoport, which is our main partner in that commercialization activities. Again, I just want to point out that every single country is eligible to apply for the incubation program. That's very important. So you are all entitled from wherever you come to be eligible. At least for the phase 1, you don't have to be present in Luxembourg. It's fully in remote. And I just want to say a word that we will open the next call for application. It will be in Q4 2025. Again, consider that one. And we are also considering the same for phase 2 for the BSGN, so the Space Resource Accelerator. I just want to say a word and thanking everyone who is part of this program, so all the ISRIC experts who are supporting in terms of in-kind support, our cluster, the big cluster that we have right now, which is currently growing in Luxembourg, and of course the 6th last batch of startups, so Polymac, Interstellar Mapping, Aphelia Space, Dow Energy Mirrors, and Imensus. All come from different countries, Malaysia, Germany, Poland, and Germany, I've said yes. The ad hoc experts who are supporting the program to make it live, to make it work, that's very important for us. Again, if you have ideas how you can support the program, we are very open to that. We cannot do it alone. ISRU is a very complex set of activities. We will be very happy to do it alone, but if you have ideas, we will be more than happy to receive your, I would say, proposal, how you can support the program, in which field. The startups need your expertise. You are all well sufficiently trained for that. And that's it on my side. Thank you very much. So if you have deeper questions, you can reach our director, Catherine, and myself. Thank you very much.
Thank you, Larry. Thank you.